working with Dr. Ian Dobbs-Dixon at the New York University, Abu Dhabi. And today I'm going to talk about two complex scattering cloud codes implemented in Retrieval. But before I start, I want to thank the organizers for giving me a chance to have a talk. I always preferred ExoClimes conferences because I've learned a lot. And in honor to that, I'm going to make a short intro about the difference between the retrieval and forward model for the graduate students present here in the audience. Okay, so there are two ways how we can approach modeling in exoplanetary spectra. One is direct, and the other is inverse. In the direct or forward modeling, which is theory-driven, we usually include all physical and chemical processes, and we use a grid of models to generate the spectra. Then the comparison is usually done with the observation by changing a limited number of parameters, and it gives us some physical insight into the planetary atmospheres. It's usually considered to be self-consistent. However, all those physical and chemical processes are usually introduced into the model without any uncertainties. So manual tweaking of the parameters are not giving us a robust estimate of the uncertainties. So it is always a question whether individual results that we are getting are the only plausible solution. On the other hand, retrieval, which is observationally driven, is a statistically driven algorithm that actually explores the phase space of the parameters and provides the uncertainties of our parameters. However, it is also very computationally demanding, and it is very hard to implement all the physical and chemical processes. It is also very hard to rule sometimes some unphysical solutions, and it strongly depends on the quality of our data and the number of data points that we have available. However, using the statistical algorithm allows us to perform a thorough exploration of the parameter space and to put the robust estimates of our uncertainties. It gives us actually a confidence region instead of the best fit model that we have in the forward modeling, and it can rule out the solutions that are not plausible by the data. It also gives us some correlation parameters, and sometimes the data can lead us to some unknown processes not yet addressed by the theory. So until very recently, clouds have been one of the most challenging issues in retrieval to implement in retrieval, although they are fundamental to understand exoplanetary spectra. So they, as we know, affect almost every aspect of planetary atmosphere, from the transport of radiation, atmospheric chemistry, dynamics. They influence the planetary surface temperature and habitability. And as we know, they highly influence the detectability of the planet because they remove the absorbers from the planetary atmosphere and they block the stellar light, so we cannot see deeper below the cloud layers. And they introduce a lot of scattered light. Until very recently, clouds have been introduced into retrieval in a very simple way. We used gray cloud approximations or opaque cloud decks. And the reason for that is, one, because of the computational intensive framework that doesn't allow more free parameters, and it introduces a high penalty on computational penalty. But the other reason is also because the current data that we have available are not of good quality, so we can actually distinguish between the more complex cloud models or the simple ones. However, with the approach of the JWST era, we are approaching a new times when there is an urge for more complex cloud models. It is because of the bigger wavelength coverage, because of the higher resolution, but also because we are at the same time developing some optimization techniques, machine learning, which allows us to perform millions of these models, to generate millions of models in a much faster way. So there is a high need for more complex models in retrieval. So I also want to give you some short introduction about what is the current state in the forward modeling concerning clouds. So currently we have two cloud approaches. One is equilibrium, approach where we actually calculate the cloud based on the intersection between the temperature and pressure profile and the condensation curves. And what you can see here on this plot are all the clouds that you can see in the solar system planets, which are calculated based on the condensation curves of the species that you can see in the solar system planets. What is interesting about this approach is that it doesn't consider something which is fundamental for formation of clouds, which is the formation of the nuclei, which are the first step in the formation of the cloud model. On the other hand, we have another more self-consistent model, which is the microphysical kinetic model that follows the formation of the particle from the top of the atmosphere to the bottom of the atmosphere. And it does consider first and foremost the nuclei formation at the top of the atmosphere. After that, it follows kinetics. It forms the particles by growing, settling, and then depletion. And then introducing convective mixing, we replenish the material from the bottom of the atmosphere and we have a stable cloud. So based on these physical approaches that we have in cloud physics, I decided that it would be good that we have both of these approaches in our retrieval framework. And we actually implemented this equilibrium approach, and we call it thermostability cloud model. That is actually a parameterized equilibrium approach. And we also have a fully self-consistent one-dimensional microphysical cloud model, which we call drift. I applied both of these models on multiple JWST targets. So let me tell you first about the thermostability cloud model. This model was initially inspired by Benek's paper from 2015 and Ackerman's Marley approach. And I also introduced some additional flexibility on the location of the cloud deck. So it has 5 pre-parameters, and it can actually address all of these cloud species if we have available high resolution NMK data. Currently, these models are addressing only one cloud species at a time. It returns the cloud profile shape, the condensate vertical particle size distribution and number density, the cloud extents, and the effective particle size. I applied this model on WAST-63b in Kilpatrick et al. 2018 paper to fit HST data. I also applied it to HD189, HD209, and some other prospective JWST targets. And recently we applied this model in submitted Venot et al. Paper on the synthetic JWST Miri phase curve observations. So to explain a little bit more about this model, I used the approach that Benek developed in 2015, where we actually can generate a different cloud shapes based on this equation here. All those cloud shapes are actually covering the cloud shapes that we can see in the solar system planets, brown dwarfs, and exoplanets, and even the gray cloud model. I calculate the cloud base based on the intersection between the temperature and pressure profile and condensation curve. And I introduce another free parameter here, which allows me to shift the cloud base depending on the number density of the gas species below the cloud deck. To calculate the cloud particle distribution, I use the Ackerman and Marley 2001 log normal distribution. And to introduce the cloud opacity in our retrieval framework, we use the Mia theory, where we calculate the extinction coefficient, accounting for the scattering and absorption coefficients. Here I'm showing you the flexibility of this model, or how well we can actually model different spectra in exostellar planets. So I'm here performing a forward model exploration for the iron and enstatite clouds, and I'm changing the particle size distribution and number density and the location of the cloud. As you can see here, for iron clouds, they affect the spectra more in the short wavelengths, while for the enstatite clouds, we can see the appearance and disappearance of the silicate feature, which is the most pronounced feature for the silicate clouds. As you can see here, just based on this simple exercise, we can distinguish between the enstatite and iron clouds in exoplanetary atmospheres. As I said, we apply this model on the WAS43 Miri phase curves, where we produce synthetic phase curve observations. Although this planet is one of the most analyzed planet so far in the recent times, there are still some unanswered questions regarding this planet, and that is the day-side redistribution. This planet, by the theoretical prediction, should have a very efficient day-night redistribution. However, the observations are telling us that the day-side distribution is actually very inefficient. And one of the reasons that we suspect could be is the existence of clouds in the night side of the planet, which would obstruct the thermal emission from deep planetary layers, producing dark flux on the night side. So that is why we wanted to investigate whether this is the case for WASP-43b. However, before that, we performed a very thorough modeling approach to predict all the possible properties of WASP-43b. We engaged radiative, convective, atmo models to predict the temperature and pressure profile, then chemical kinetics from Venot, then to predict the chemical composition. Then we used cloud microphysics from Peter Gao, and using all those predictions, Vivian ran his global circulation models without clouds, and then he attached the passive clouds after the GGCM run. Then we used some of those models in Pendexo to generate the data with uncertainties. And finally, we performed the spectral retrieval for cloud-free, quenched, and cloudy models. My task here was to do retrieval, cloudy retrieval. As I said, I use Vivian's model with passive clouds for ancetine and MNS clouds. The data were produced with Pendexo for the particle sizes of 1 micron. In the same time, we also asked our ex-group, Waldman et al., to do the same exercise. And the goal was to retrieve the correct particle size, cloud number, density, and location of the cloud deck. Also to distinguish whether we can make a distinction between the MNS and magnesium silicate clouds. Here I'm showing you the GCM models from Vivian for different particle sizes and for clear and cloudy cases for magnesium and MNS clouds. And in dots are actually Spitzer and HST data, while the triangles are JWST data. And just based on these models, we made some predictions that ancetite clouds we can see on the day and the night side, while the MNS clouds can only be seen on the night side. Then we use some of these models to generate these data that I used in retrieval. These are the uncertainties data with uncertainties, and in magenta is our Vivian models. So as I said, we also called the TowerX team to try to retrieve the particle size. However, their cloud model was not complex enough to retrieve the correct particle size and the location of the clouds. So they were unsuccessful, but on the contrary, we were very successful in retrieving the correct particle size, the location of the cloud, and the number density of the cloud. What I'm showing you here is the best fit model, the temperature and pressure profile, and the condensation curves, which actually reveal you the location of the clouds. Here you can see the correlation plots and the histograms, how we retrieve exactly 1 micron as Vivian's input model and the number density of the particles. For the MNS clouds, we have the similar results where we retrieve somewhat different, a little bit larger particle size than the input model. And we also performed 2 different retrievals. We performed the free and self-consistent retrieval. What we concluded from these analyses is that it's very important to have more flexibility in our cloud models so we can actually model some features in our data. So being able to model, to have more free parameters will allow us to model better the data from the JWST and MIRI. I also wanted to briefly talk about my other model that we have in retrieval. We implemented a fully self-consistent one-dimensional microphysical kinetic model from Boytke and Helling et al. 2008. This model has 4 parameters: overshooting or mixing parameters that defines the condition in the convective radiative boundary, then convective radiative boundary pressure, carbon to oxygen ratio, and metallicity. It can cover several nuclear species and many various dot species, and it returns the nucleation rate of considered nuclei species, effective particle size, dust volume composition, location of the different clouds, which are spread on the vertical direction, and depletion of the elemental species. Here I'm also showing you some exercise on how different, how changing some of the parameters of our drift model can affect the spectra. As you can see here, this is the change in metallicity, and here we are changing actually the mixing coefficient, and we can see the appearance and disappearance of silicate features as well. I perform a forward modeling exercise with drift model here. Here I'm showing you HD209 model and data from Singh et al. 2016 paper. And here I run drift model for cloud-free and cloudy solution. And here we are almost matching. The spectra are very similar with the Singh et al. Model, but based on, thanks to our self-consistency of our model, we can also produce the location of where the nucleation rate or where the nuclei are mostly formed. Then we produced also the effective particle size, which is changing if we go deeper in the planetary atmosphere. We also can produce the cloud shape, which means where is most of the mass of the cloud actually located. Then we can see here which clouds are actually formed in different parts of the atmospheres, which cloud species are formed in different parts of the atmosphere, and finally, how the elemental abundances are changing. So as a takeaway message, I just want to point out the importance of different cloud models that we should have for the expecting of the JWST era, which are going to have a higher resolution and wider wavelength coverage. The importance of the flexibility of our models, so we can actually cover different features in our clouds. And as I said before, this model that we have in our retrieval framework is allowing us to differentiate between the different cloud species seen in the spectra and to differentiate which is most dominant species seen in the spectra, while drift model that we have are telling us about the aggregate clouds and the total contribution from all the cloud species to the spectra. Thank you.
Nick Cowan, McGill University. Is this only for transmission spectroscopy, or can you also do reflected light?
I can do both. Oh no, I cannot do reflective light.
You can't do reflective light yet. No. Okay. Can you do thermal emission? Like, yes, do these clouds? So these clouds can block OLR. They just don't reflect.
Yes.
Shortwave.
They do have. So if you saw in this parameterization, the Mie scattering code does have the reflective contribution from scattering and reflective efficiencies. So we do calculate the scattering efficiencies in our cloud model for the Mie scattering code, in the Mie scattering code.
Elena Manjavacas, Keck Observatory. So thank you for the introduction. First of all, it's not only useful for grad students, but also for other people like me. So you say always, and many people doing retrieval say the same thing, that you don't have data with enough quality to test your retrievals. But there are like on the order of 100 HST spectra for brown dwarfs that have very good quality. and that might be useful for you to test your retrieval. So I was wondering, why don't you use those?
So most of the spectral features are actually coming from the infrared region. So we are actually hoping to have more insight into the longer wavelengths, because the vibrational and rotational states of the molecules are producing more spectral features in this region rather than where AGST data are from.